Hi, my name is Kelsey McClure, and I'll be talking to you about our project, a large-scale machine learning model for predicting postoperative morbidity in laparoscopic and open cholecystectomy. I have nothing to disclose. So as surgeons, we all understand the importance of providing patients with the risks and benefits of the procedures that we perform. We have reached an era where providing individualized risk-benefit analysis is possible. We have also reached an era where the amount of data collected in healthcare systems has surpassed the capabilities of standard statistical methods for optimal analysis. The NSQIP calculator is a popular tool to help evaluate individualized risk, but it utilizes only a small fraction of the data collected, and it lacks the ability to evolve with increased data. We propose using machine learning, an emerging technology equipped to evaluate large quantities of data to create a more accurate predictor of postoperative outcome. So what is machine learning? At its most rudimentary level, machine learning is an algorithm, or a systemic set of operations to perform on a given data set that is given a teaching set of data, various inputs with known outputs within a larger data set. The algorithm is then tested using new inputs and judged by how accurately it predicts outcomes. After the model is built, you can use it as a classifier. When new data comes in, it's fed through the model, and a predicted outcome is made. Machine learning is all about predicting patterns, which has obvious implications for medicine. There are a variety of methods used in machine learning to assess large quantities of data. For our project, we used decision trees and random decision forests, which are ensemble learning methods. Or in plain English, they start by evaluating data with known inputs and outputs, and the algorithm then uses the data to construct a set of greedy rules to make decisions. For example, on the right is a tree showing survival of passengers on the Titanic. I like this example because everyone can understand that there are already known outcomes for each passenger. They either lived or died. As you can see, this is a very simple decision tree with several branch points. The first is whether or not a passenger was male. The second asks how old the passenger was, older than 9.5 years old or younger. The third asks about the number of family members traveling with the passenger. Did they have a spouse or a few kids on board? The numerical values represent the number of the percent of passengers fitting within that decision line. Summarizing, your chance of survival were good if you were 1, a female, and 2, a young boy without several family members. Part of the creation process of the machine learning algorithm helps us to know the important branch points or the most important factors in determining the outcome. In this simple depiction, you can see the rudimentary steps to create a group of decision trees. Together, data from many trees creates a construct called a random forest. This is an example of what is called an ensemble method, since we are collecting many groups and putting them together in an ensemble. 2 main points here. First, to make good trees that generalize well, you need a lot of data on a lot of people. And second, the more trees you have, the better the predictive value. Everyone is familiar with the NSQIP database. Since NSQIP conveniently has a risk calculator and a large database, we chose to use the same databank to see if we could build a better model using machine learning. We pulled all of the cholecystectomy cases from NSQIP. Then, using the machine learning techniques I described, we used the data to create an algorithm to predict postoperative morbidity. First, we take the raw data from NSQIP, cholecystectomy cases identified by CPT codes. Then the data needs to be cleaned. All cases with incomplete information are removed, leaving a clean data set. The independent variables used to build the model are selected. This is a very complex process that I will not get into for the purpose of this talk. Then the data is processed for input into the model. Second, to build our model, we have both known inputs and known outputs, real patients with known comorbidities, inputs, and known outputs, postoperative morbidity. Then, using the machine learning techniques I described, we use 80% of our database to create a robust algorithm that will accurately predict outcomes. We save 20% of our data to test the algorithm. Then, using the remaining 20% of the data as inputs, we measure how accurately our model predicts the known outcomes. This provides a blind test for model performance. In our study, 17 postoperative morbidity outcomes were combined into a single binary output variable, either the occurrence of a morbidity or no occurrence. The NSQIP database has over 4.2 million cases and more than 250,000 cholecystectomy cases, most of which are performed laparoscopically. As you can see, there is a much higher risk of postoperative morbidity if the cholecystectomy was performed open. Just as the example I gave earlier identified the features most likely to lead to a passenger's mortality on the Titanic, our model was able to identify the top features associated with postoperative morbidity after cholecystectomy. Using the same statistical analysis that was used for the NSQIP surgical risk calculator, C-statistic, which describes the overall accuracy of the model on a 0 to 1 scale, where higher is better and a score of 1 is a perfect prediction, and the Breyer score, which quantifies the closeness of each individual prediction to the actual outcome on a 0 to 1 scale, where lower is better and a score of 0 is a perfect prediction, you can see that our model, using machine learning techniques, outperforms the NSQIP surgical risk calculator in its ability to predict postoperative morbidity following cholecystectomy, i.e., our C-statistic is closer to 1 and our Breyer score is closer to 0. So in conclusion, we were able to develop an algorithm using machine learning techniques that uses all of the data within the NSQIP database and outperforms the NSQIP risk calculator. Models such as this one can be used to provide empirical informed patient risk scores for postoperative morbidity. The analysis also provides a determination of the most relevant factors predicting patient risk in cholecystectomy. We've entered an era where classical statistical methods are unable to analyze the vast amount of medical data collected. We need to embrace new technologies as a means to analyze these larger data sets. And I'd just like to thank my partner and the brains behind the operation, Stephanie Moorman, and my program director and associate program director, Dr. Scott Peterson and Catherine Cohen, and the St. Joe's Surgery Department.